Good morning, friends. Now, how the sound waves are propagated in a medium. Today we are going to discuss about the propagation of sound waves in a medium. Right? So the question is that explain the propagation of sound waves in a medium. We know that when the sound waves are propagated in a medium, the oscillation of particle of the a medium take place along the direction of propagation of the wave. That means the longitudinal waves are produced during the sound waves are propagated in a medium. So as a result, in some region of the a medium, the a particles are compressed. That means comes close to each other. As a result, the density of this region is going to increase. While in the some region, the air particles are quite separated. That means in this small region, the density is decreased. As the density increases, so pressure of the region increase, decrease, this way take place. But the air medium is the elastic medium. Due to the pressure increase in some region, pressure decrease in some region, the stirring force is also generated. This stirring force again bring back to the air medium particle in its equilibrium position. As a result, the oscillation of air medium take place, and this way the sound waves are propagated in air medium. Here we are going to discuss this thing in detail. As the sound wave passes through the air, compression and expansion of the small region of a medium take place periodically. That means that when the sound waves are propagated, so a medium particle of the a medium oscillate. So as a result, in some region, the air particles comes together. Therefore, the compression take place. While in the next region, the particles of the a medium are going away from each other. That means the expansion take place. Right? This expansion and compression take place periodically along the direction of propagation of the wave. In the same direction of propagation of the wave, the expansion and compression is take place periodically. A small region in which the compression take place, causing the increase in density. That means the region in which the compression take place, in this region the density is increased, and hence the pressure delta P is also increases according to the equation of an ideal gas. Density increases, therefore the pressure of this small region is also increased. How the pressure is increased? So according to the equation of state for the ideal gas, PV is equal to mu RT for the nRT. Okay, V is the volume, P is the pressure, I is the constant, and T is the absolute temperature. Now we know that density rho is equal to mass per volume. Therefore, volume is equal to mass upon density. Substitute in this equation, therefore P into M upon rho is equal to nRT. Therefore, the P is equal to nRT upon M into rho. N is constant, I is constant, T is constant, and M is also constant. Therefore, P is directly proportional to the density. As the density changes, so pressure of this region is also increased with the change. So the small region in which the compression take place, in this region the density increases, as a result the pressure is also increases. Clear this thing? Okay. Thus, during the propagation of a sound wave in a medium, the compression and expansion take place periodically. The region in which the compression take place, the density of this region is increased, and as a result, the pressure is also increased according to this equation of an ideal gas. Now, in such a high pressure region, density is increased temporarily. This is known as the condensation. This region is known as condensation or the compression. It is denoted by C. Here the two figures are shown. During the propagation of the sound wave in a medium, this region in which the air particles comes together, therefore the density and pressure of this region is going to increase, and this region is known as the condensation or the compression. It is denoted by C. Now the next small region in which the numbers of the air particles are less, therefore the density is less, pressure is less, and that is known as the rarefaction. That is known as the rarefaction. How the rarefaction is formed? This way. In such region, the destroying force is developed, which is directly proportional to the displacement of a particle from its mean position. Here, the pressure increase. Pressure is what? The force per unit area. Area of this region is constant. Therefore, the force is exerted on what are the gathered air particles, and that is the destroying force. Destroying force in this region is developed, which is directly proportional to the displacement of a particle from its equilibrium position. In such region, the particle has the tendency to move outwards, and the density decreases temporarily. So when the sound waves are propagated in the air medium, at that time, first in small region, the particles are gathered. As a result, the compression takes place. Next region, expansion takes place. In the region in which the compression takes place, density and pressure increases. Pressure is the force per unit area. So due to the compression of the air particle, destroying force developed between the particle. This destroying force has the tendency to move away the particle. As a result, the particles are going away from each other. Therefore, the region in which the compression takes place, now in this region, rarefaction takes place. That means the density decreases, pressure is also decreases. Thus, the density decreases temporarily. In such low pressure region, rarefaction or the expansion is formed. First, the compression or the condensation formed. After some interval of time, in the same region, rarefaction or the expansion takes place. Right? It is denoted by capital R. Each small region of a medium coming successively in the direction away from origin of sound. So this way, compression, expansion, or the condensation, rarefaction take place successively in the direction of the sound wave going away from the source. Thus, the sound waves propagate in a medium, and sound waves are mechanical and longitudinal. So there is the propagation of sound wave in a medium. The sound wave propagate in a medium in the form of condensation and rarefaction. The region in which the compression or the condensation takes place, in this region, density as the pressure increases. According to the equation of an ideal gas, PV is equal to mu RT. Now the pressure in the compression or the condensation region is more. Right? Pressure is the force per unit area, which produces the destroying force on the gathered air particles. Therefore, the air particles has the tend to go outward. Therefore, the air particles now going in this direction. As a result, what's happened? In the same region, the density decreases, therefore the pressure is decreased, and hence the rarefaction or the expansion takes place in this region. And the density of this region decreases temporarily. Thus, the formation of the condensation and rarefaction take place periodically during the propagation of sound wave in a medium. Clear? The sound waves are mechanical and also the longitudinal wave. So there is the propagation of sound waves in a medium. Right? Okay. Now, after the discussion of the propagation of a sound wave in a medium, now how the sound waves are propagated in a solid or the metallic wave. For that purpose, first we have to understand about what is the structure of the crystalline solid. Now, the crystalline solid possesses the lattice structure in which the atoms of the molecules are arranged with the some definite geometric pattern. Right? That means in a solid, here all the particles of the solids are arranged in regular manner like this way. These are the atoms of the solid. Here the definite regular or the periodic pattern, geometric pattern, the atoms are arranged. Here the intermolecular force is exerted between the atoms and molecule. Therefore, all these atoms are in equilibrium position. Right? That is the crystalline structure of solid. Again, the crystalline solid possesses the lattice structure in which atoms or molecule are arranged with the some definite geometric periodic pattern. In normal condition, without any disturbance, all these atoms of the molecules are in equilibrium position. So, as we are not applying any force or any disturbance in this solid, so all the atoms are in equilibrium position. Because the forces exerted from the surrounding balance each other. Due to the intermolecular forces exerted between each other. Therefore, all the atoms of the molecules in crystalline solid are in equilibrium position when the no disturbance is entered or the no disturbance produced in this position. Clear this thing? Again, what is the crystalline structure of the solid? Crystalline solid possesses the lattice structure in which atoms of the molecules are arranged with some definite geometric periodic pattern. In normal condition, without any disturbance, all these atoms or molecules are in equilibrium. Because the forces exerted from surrounding balance each other. Due to the intermolecular forces exerted between the molecule or the atom, all the atoms are in equilibrium position in a lattice structure of a crystalline solid. Now, if the disturbance is produced in any atom or the molecule, it gets displaced from its equilibrium, and these atoms or the molecule elastically connected with neighboring atoms. Suppose we produce the disturbance on this atom. So what's happened? It disturbs from its equilibrium position and start the oscillation about their mean position. Now, this atom is connected elastically with its neighboring atom. Hence, the strain force is developed in such imaginary elastic spring. Therefore, so this atom start the oscillation due to the disturbance act on it. But this atom is connected with its neighboring atom with elastic or the elastically connected. Therefore, due to the oscillation, the strain force produced by the neighboring atom on this atom. Such a force is responsible for producing very small oscillation in these atoms or the molecules, turn by turn, along the direction of motion of disturbance, which is the propagation of sound. So here what's happened? The disturbance is exerted on this atom So as a result, that is connected elastically with its four neighboring atoms. Right? Okay. Due to that, the historic force is exerted on neighboring atom. Therefore, neighboring atom will also start the oscillation about their mean position along the direction of the disturbance. Suppose we apply the disturbance in this direction on these two atoms. So these two atoms are connected elastically with its neighboring atom. So due to the historic force exerted on neighboring atom also start the oscillation about their mean position. Again, the effect of this oscillation is transferred to the neighboring another atom. So another atom also start the oscillation about their mean position. Thus, the disturbance is propagated along the direction of oscillation, and that is the propagation of sound waves in the solid medium from one end to the other end. Clear the same? Again, in a crystalline solid, the crystalline solid possesses the lattice structure in which the atoms of the molecules are arranged with some definite geometric periodic pattern. In normal condition, without any disturbance, all these atoms of the molecules are in equilibrium because of the forces exerted from the surrounding balance each other. So that is the crystalline structure. All the atoms are in equilibrium because all the atoms, any atoms, is surrounded by the neighboring atoms, and neighboring atoms apply the intermolecular forces on each and every atom. Therefore, all the atoms are in equilibrium position as the disturbance is not entered or not in absence of disturbance. If the disturbance is produced in any atom, we apply the disturbance here. So what's happened? These atoms start the oscillation. And all these atoms are connected elastically with its neighboring atom. So due to the historic force or the elastic force exerted between the atom, the effect of this oscillation takes place or the transfer to the neighboring atom. Therefore, the neighboring atom also start the oscillation. And then this effect is transferred to the another neighboring atom. So if the disturbance is produced in any atom or the molecule, it gets displaced from its equilibrium, and this atom or the molecule elastically connected with neighboring atoms. Hence, the historic force is developed in such imaginary elastic spring, and such force is responsible for the producing very small oscillation. Whatever the elastic force is exerted between the molecule, this historic force is responsible to produce the small oscillation in the atom or the molecule, turn by turn along the direction of propagation of the wave, which is the propagation of sound wave in solid medium. Now listen, the sound wave can propagate for the long distance in air medium, right? But in solid, the sound wave cannot travel the long distance in solid. Because in solid, the distance between the molecule is less compared to the air medium. And also, here due to the intermolecular forces between the molecule or the atom is strong compared to the air medium. Therefore, the sound wave do not travel the long distance in solid. That means the sound wave is not sustained for the long time in a solid. Clear the same? Now, explain the types of the waves on the basis of the oscillation of particle of the medium. Already we classified the waves in three categories: mechanical, non-mechanical, and also the matter wave. Now, the classification of wave on the basis of oscillation of the medium, particle of the medium. On the basis of oscillation of particle of medium, the mechanical waves are classified in two categories. One is transverse wave and second is the longitudinal wave. What is the transverse wave? During the propagation of mechanical wave, if the particle of the medium oscillate perpendicular to the direction of propagation of the wave, then such waves are known as the transverse wave. Suppose the waves are propagated in this direction. During the propagation of wave, if the particle of the medium are oscillate perpendicular to the direction of propagation, like to this way. If this particle are oscillate like to this manner, that is the direction of motion of a wave. And if the particle of the medium oscillate perpendicular to the direction of propagation of wave, such waves are known as the transverse wave. Right? Now, what are the waves produced in a string? The waves are propagated in this direction like this. So, the particle of the string are oscillate perpendicular to that in this direction like that way. So, as we drop a stone in a water, so what are the waves are generated in a water? There is also the transverse wave. Now, the waves in a string, the water waves are the mechanical waves, while the non-mechanical wave, light wave, is also a transverse wave. Transverse wave. Already we discussed about the light wave, electromagnetic waves. Electric field and magnetic field oscillate perpendicular to each other and also perpendicular to the direction of propagation. Therefore, non-mechanical wave, all light waves, is also a transverse wave. Again, the definition of the transverse wave: during the propagation of mechanical wave, if particle of the medium oscillate perpendicular to the direction of propagation, such waves are known as the transverse wave. Now, example of the transverse waves are waves in a string, water waves are the mechanical wave and also the transverse wave, while the light waves, like as the gamma rays, UV rays, X rays, are non-mechanical wave but also a transverse wave. Now, next is, what is the longitudinal wave? Already we discussed when we discussed about the sound propagation of sound wave. For that purpose, during the propagation of mechanical wave, if the particle of the medium oscillate parallel to the direction of propagation of a wave, here the oscillation of particle of the medium perpendicular to the direction of propagation of a wave, here the oscillation of the particle of the medium parallel to the direction of the propagation. Such waves are known as the longitudinal wave. Sound waves are mechanical and also the longitudinal wave. Already we discussed about that. There is the direction of propagation of a sound wave. The sound waves are propagated like this way. Condensation, rarefaction, condensation, rarefaction. Therefore, the medium of the particle also oscillates along the direction of propagation of a wave. Thus, the sound wave is mechanical wave and also the longitudinal wave. So keep in mind the difference between the transverse and longitudinal wave. Transverse wave, the oscillation of the particle of the medium take place perpendicular to the direction of propagation of a wave. Example are waves in a string, water waves are the example of mechanical and also the transverse wave. While in longitudinal wave, the oscillation of the particle of the medium along the direction of propagation of a wave. Such waves are known as the longitudinal wave. Example is sound waves is mechanical and also the longitudinal wave. Clear this thing? So this is the classification of the waves according to the oscillation of the particle of the medium. Clear?